In this video, we're going to look at the solution process, and before we get into that, I just kind of want to bring up something here. When we can dissolve various substances in water to form aqueous solutions. So at 25 degrees Celsius, 359 grams of sodium chloride will dissolve in 1 liter of water. But if we took silver chloride and tried to dissolve that in water, only 0.00186 grams are going to dissolve in the same volume of water. So why such the big difference, and how can we account for this particular difference here? So a process in which the energy content of the system decreases tend to occur spontaneously. And when a substance dissolves, we must consider, and there are two main things that we need to consider. Number one, what forces need to be broken in the reactants? And number two, what forces are gained in the formation of the product mixture? And the question is, are we gaining something from the formation of this product or the formation of this solution? To describe what happens when a particular substance dissolves, we typically have a solvent, which we'll say is water in this case, but we'll use an aqueous solution, plus a solute, which is typically a solid. And the question is, will we form a solution? Or will that solid solute dissolve in the water? Okay, so we can kind of look at various aspects of this. Okay, in the solvent, we're going to have energy required to break the intermolecular forces in the solvent. And we'll call this delta H of the solvent. So there's going to be energy required to break all the intermolecular forces that are combined in the solvent, because that solvent solution is going to have all its molecules that are attracted to each other. We drop this solid in, what happens? Okay, we are going to require energy, or energy is going to be required to break all the intermolecular forces or bonding network in the solute. And we can call this the delta H of the solute. Both the delta H of the solvent and the delta H of the solute are going to require energy for these to happen. Okay, so if we're requiring energy here, we better gain energy somewhere. Okay, so the energy that's going to be gained comes over here from the solution mixture. So the energy gained when we form new intermolecular forces between the solvent and the solute. And we'll refer to this as the delta H of the mixture. Okay? So, in this particular case, everything over here on the left, or in the reactants, is going to require energy, and everything over here on the right, which is the delta H of the mixture, is going to gain energy. So we need the energy gained from the mixing to be greater than the energy required to destroy the intermolecular forces for the solvent and the solute. So overall, we can write this reaction as delta H of solution, which is the whole solution process, is going to equal the delta H of the solvent plus the delta H of the solute plus the delta H of the mixture. And this is going to help us predict whether or not this particular dissolving process will happen. So if you remember back from chapter 5, the statement there is when delta H is negative, a reaction tends to proceed spontaneously. So we need to figure out here, when is our delta H of solution going to be negative? Okay, so if we look over here in these two circumstances, if the delta H of the mixture is greater than the delta H of the solvent plus the delta H of the solute, then our delta H of our solution is going to be a negative value, and this is going to be favorable. Okay? On the other hand, if our delta H of the solvent plus the delta H of the solute is greater than the delta H of the mixture, this means that our delta H of our solution is going to be positive, and this is going to be unfavorable. So by looking at the various, magnitudes of the energy here required to break intermolecular forces and form new intermolecular forces, we're going to be able to look at a particular process and determine whether or not it's going to be favorable or unfavorable.